G'day everyone, and welcome back to Lubrication Explained. Today we're going to be talking about the different API groups of base oils. So you've probably heard people talk about Group 1, Group 2, Group 3 base oils. So we're going to discuss what they are and what that means for you. So the ones that you're probably most familiar with are these three groups. So Group 1, Group 2, and Group 3. And these are kind of the mineral oils. Now, something that distinguishes the mineral oils is their saturate content, sulfur content, and their viscosity index. So what does that actually mean for the different groups? Let's talk about saturates first. So a saturated hydrocarbon is one that doesn't have any double bonds. So as an example, you have an ethylene molecule, or ethene, that's got a sort of a carbon-carbon double bond in it. And the problem with carbon-carbon double bonds is that they are relatively oxidatively unstable, so they are subject to attack. And this is why when we manufacture lubricants, or specifically when we refine them, we try and remove as many of those double-double carbon bonds as possible through a process of hydrocracking. And that will give you an ethane molecule, which is much more stable. So this is, with only two carbons, the simplest version of saturating a hydrocarbon that I can give. But you can obviously do that for any length of hydrocarbon chain. So the saturate content varies between Group 1 and Group 3. Then we move across to sulfur, and you might ask, where does the sulfur come from in a base oil? So if you remember, and I'll cover this in more detail in another video, all mineral oils start their life as crude oil that comes out of the ground. So that's kind of what defines a mineral oil. And within crude oil, there are an infinite combination of different molecules. And some of the molecules that I'm showing here below are the ones that contain sulfur. So often there'll be aromatic compounds, so they're the ones with the benzene rings. They will contain sulfur. But there are also, sulfides and thiols, as well as disulfides. And these are all sulfur-containing compounds. We try and remove those through a desulfurization process as we move from Group 1 to Group 3. So remember, as we're moving from Group 1 to Group 3, we're effectively it's more refined, if you like. Finally, there's the viscosity index. And again, this is one that I'll talk about. It'll get its own standalone video. But basically, the viscosity index is the measure of how much does your viscosity change with temperature, right? So like other Newtonian liquids, lubricants tend to be thick when they're cold and thin when they're warm. And the degree of that change gives you your viscosity index, where a higher viscosity index is more desirable. So that's the mineral oils, Group 1 through 3. Below those, we've also got Group 4 and Group 5. Now, Group 4 are all what we call the polyalpha olefins, and they're a class, the most common class of synthetic lubricants. And Group 5 is all the others. Now, one of the maybe misnomers is that Group 5 is all synthetic. That's not entirely true, so let's explore that in a little bit more detail. Synthetic oils can actually come from either Group 3, Group 4, or Group 5. And that's for some different reasons. So let's look at Group 4 first. They are all the polyalpha olefins, which are, by definition, all synthetics. So if you have a lubricant that is manufactured from Group 4 base stocks, it is by definition a full synthetic. However, if you have a lubricant that comes from Group 3, it may also be marketed as fully synthetic. There was actually a court ruling in 1999 in the US, which kind of governs how products can be marketed in the consumer space. So typically, if you go and you buy what is called a full synthetic engine oil from the shop for your car, it may be a very heavily refined Group 3, because the legal determination was that synthetic, when it comes to the consumer segment, refers more to the performance of the lubricant as opposed to the way it was manufactured. So this is why some group 3s, when they're heavily refined, can be referred to as full synthetic. Then we come to group 5. Now group 5 is tricky because it does contain some full synthetics. Polyalkylene glycols, also known as PAGs, are an example. Alkylated naphthalenes, for example, synthetic esters. These are all full synthetic molecules. However, group 5 also contains things like white oils, or the paraffinic base oils, or the silicon-based base oils. And those are neither mineral nor fully synthetic. Right? So group 5 does contain some synthetic base stocks, but not all group 5s are synthetics. I hope that clears that up. So let's concentrate on the mineral base stocks for a little bit. Synthetics we'll have to go into a little bit more detail because the way that they're manufactured is very different. But if we concentrate on the minerals, let's look at some of the different properties and how they are affected as you move between the groups. So for example, solvency. This is a really interesting one. So solvency is highest for group 1. And the reason is because solvency is kind of a measure of the polarity of all the molecules within the base oil. And group 1 base oils have the most polar molecules. So especially all those aromatics, they are kind of highly polar. And that helps with solvency. Now, solvency is important for 2 reasons. First, because you need a certain amount of solvation to be able to get your additive package to go into solution within the base oil. But also, and this is important for turbine oils in particular, varnish precursors tend to stay in solution for much longer in a group 1 than they do in a group 2 or group 3. And that, in some ways, the move from group 1 to group 2 and 3 turbine oils is one of the reasons we are seeing more incidences of varnish in industrial gas turbines. Oxidation stability. Now, this one's a bit of a tricky one. So, the amount of sulfur, and specifically aromatic sulfur, within a base oil kind of gives it some inherent oxidation stability. And therefore, for the base oil at least, the group 1s are more inherently oxidatively stable. Now that probably goes contrary to everything that you've heard about your lubricants. You've probably heard that the group 3s are much more oxidatively stable than group 1s. And that is actually true of the finished lubricant. So why do they go in reverse? Well, in a virgin base oil, group 1s, because of their sulfur content and the aromatic content, are more inherently oxidatively stable. However, when you create a finished lubricant, we put antioxidant additives into the finished lubricant, and they work better in conjunction with a group 2 or group 3. So as a result, the finished lubricant of a group 2 or 3 has more oxidation stability than a group 1. So that's one that's a little bit counterintuitive. We've also got the viscosity stability. So that is the viscosity index, and we know that group 3s have higher VIs than group 1s. And that's also related to the pour point as well. Finally, we've got toxicity. Now, it's the aromatic compounds with their benzene rings which are the most toxic components of a crude oil. So we generally remove these as part of the refining process, and therefore group 3s are lower in toxicity than group 1s are. The other way that we can think of this is in maybe a different space. So let's take a triangle and talk about the relative content of paraffins, aromatics, and naphthalene. So what these look like is, sort of chains with benzene rings and chains with a single aromatic ring. So if we were to map where do group 1s kind of sit in this triangle, they sit roughly in the middle. right? So this is where a group 1 would sit. So it has a decent amount of aromatic content, some naphthenes and some paraffins. As we more heavily refine it and we remove some of those aromatics and we convert some of the naphthenes into paraffins, we move to group 2 base oils. Then as we heavily refine it again through more severe hydroprocessing, we end up with group 3s. And finally, group 4s, or the PAOs, are fully paraffinic. So by definition, they are made from molecules which are paraffins, and you end up with a finished lubricant which is 100% paraffinic. So that's where the group 4s, also known as the PAOs, sit. So I hope that this has kind of given you a bit of a flavor for the different API base oil classifications. I'll go into more detail about how these are manufactured in other videos, but hopefully this has given you a bit of a flavor for how to recognize the different base oil groups and what that might mean for your finished lubricant. Thanks for listening. This has been Lubrication Explained.